into the derivative. Okay, so these I call test points, right? These are test points. And these test points now get plugged into the derivative. So let's do that as like a fourth step. Plug test points into derivative. So I want f prime of -3. I want f prime of 0, and I want f prime of 4. See, I'm saying, hey, look, what is the derivative doing over there to the left of -2, right? Over here, what's the derivative doing? What's the derivative doing here? What's the derivative doing here? So at -3, I plug into that, into this. That's going to suck. Okay, -6 times -3 squared plus 6 times -3 plus 36, and you get, I don't know. It's a negative number. Do you believe me? You just do that arithmetic. This is a negative number. Then if you plug 0 in, I think 0 is a little easier, right? What happens if you plug 0 in here? Kills that, and you just have 36, right? So that's a positive number. And then if I plug in 4, again, I hope you'll believe me that it turns out to be a negative number. Are y'all all right with me not plugging those in and leaving that to you? Is that all right with you? Yeah? All right. So let's see if we can analyze this and understand it. To the left of -2, what's my derivative doing here? What's my derivative? It's negative, right? The derivative is negative, which means what's decreasing? The original function's decreasing, right? The derivative being negative means the original function decreases. So what I'm going to do is over here in this region, I'm going to put f is decreasing here, right? The function's going down here. Why? Because the derivative's negative. All right, what about 0? Here, that's between these two, right? My derivative there is positive, isn't it? Which means the original function is increasing there. So my original function is going up. And then finally, at 4, that's over in this region, my derivative is negative, which means my original function is going down. So my function is going down, then up, then down, right? Down, then up, then down. Do y'all see what's happening here then at -2? I should have what there? A local min should be happening here, right? And then it goes up and then down, up and then down, right here. At 3, I should have a local max, right? So this little chart, table, whatever you want to call this, answers part A, B, and C. All of it is answered with that picture right there. So let me answer part A. For part A, I was asking for what? Where's it going up, right? So now I'm answering questions. So part A, that's not A, that's a 1. Part A, I wanted to know where the function was going up, right? So I'll put a colon here. Let me tell you where it's going up. Now, when I tell you where it's going up, yes, question?
So you said that 3 was going to be the local max?
Yes.
And now you're choosing the local min?
Yes.
Because that's the smaller of the values.
No, because I know what the graph's doing. Do you see that over here I'm telling you the graph goes down? And then over here it has to go up? So if you go down and up, then you've got to be down like at a valley, right? So it's got to be a local minimum. And then over here it goes up, and then it comes back down, which means you got to have a local max there. Has nothing to do with the fact that that's a negative number. It has to do with this shape.
And we could potentially have more than 2?
Oh yeah. Oh yeah, you could have more than 2. You could have none. You could also have none. Okay, so I want to know where the function's going up, right? Where is it going up? Do y'all see that it's going up right in this little region? That's the only place it goes up, right? So how do I tell you that? I'm going to give you the answer in what's called interval notation. I'm going to give you these x values Everything between here and here is where it goes up, right? So I'm going to write it like this. -2 to 3. Now, just understand, these are x values. These are x's that I'm giving you. If your x value is between -2 and 3, I guarantee that the function's going up over there. Between that, on that interval, the function has to go up. Good or no? Any questions? Part B, where's the function going down? Well, it goes down over here, right? Forever that way. And then here, that way. Forever. So how do I say that? How do I say forever that way, but then stop here at -2? Negative infinity to -2. So this answer is going to be -infinity to -2, parentheses on both. Never put a bracket on infinity because it's not a number. So -infinity to 2, and then the other interval was what? From where to where? 3 to positive infinity. And I want both of these intervals, right? So what's the symbol we put in between here? A capital U, like a union symbol, like this. That means the union of those two sets. Just take a step back. Does it make sense to you what these things are saying, right? My graph's going up when I'm in here. My graph's going down when I'm here or here. Yes?
Do you need to worry about brackets on the like actual values like -2 and 3?
Are you saying including these endpoints? No, just always don't include them. That's the safest thing. Just don't include them. It's not wrong if you don't include them. The book might put a bracket there. Yeah, let's not get into it. Yeah. All right, so C, part C. Part C was local maxes and mins, right? So we have, how about local maxes? Do we have any local maxes? Where? At 3, right? Right? At x equals 3, the graph goes up and then down. So that's a local max. So what I'd like to do then is I'd like to actually know how high it goes, all right? How high does that graph actually go? How could you figure that out? Take that number and plug it into the original function. Wouldn't that give you that peak? Yeah, so let's do that. So when you plug 3 into the original function, which I've erased now, we get some number. I'm going to do it on the computer, all right? And then we should have a local minimum. Where should the local minimum be happening? At x is what? -2, right? And that means if I plug -2 into the function, I can get the actual value, all right? So let me now come over here to the computer, and we're going to see if what we did makes sense with Desmos. (2x cubed), oh wait, minus 2x cubed. All right, there's the graph, which doesn't look very good. So I'm going to zoom it out here. Let me see. Okay. So there's the graph. Can you all see that all right? Do you all see that it looks like we have that to the left of 2, right, -2, sorry, to the left of -2, my graph is decreasing, right? And then where else is it decreasing? To the right of 3, it decreases, right? And then between -2 and 3, it increases. We have a local minimum here at -2, and we have a local maximum at 3. Now to actually find the values, I have to plug those numbers in, which I didn't do. So let me go to 3 and I'll have the computer do it. You get 81, okay? So you get 81 if you plug 3 into the function. And then if you plug in -2, you get -44. Do y'all see how much information we can gather from the derivative? Right? Like back in college algebra, when you were graphing polynomials in college algebra, you never were able to find these lowest and highest points. You couldn't do it. You actually need the derivative to do that. And we're demonstrating that right now. Any questions? Let's run through the procedure again. We took the derivative, right? We found the critical numbers. Then we did a number line, right? We did test points. Then we plugged those test points into the derivative, and that gave us everything we needed, right? We plugged the test points into what? The derivative. We plugged test points into what? What did we plug the test points in? It's 3 times. 3 times we've said that, right? That's the reason I'm saying that is because in 4.1, you find the critical numbers. You don't do test points. In 4.1, when you're on a closed interval, you find the critical numbers, and you plug the critical numbers into the original function. That's the method. It's a different thing we're doing there. And so students, what happens is they confuse the 2 methods. And they take the test points and they plug the test points into the wrong thing. Right? So let's do another example, and let's do a harder function. All right? This is a polynomial. Let's do something more mathy. Okay? Something that's a little more like calculus. Like it feels like calculus. A function that we don't know what it looks like, just right off the bat, we don't know what it looks like. Like that was a polynomial. You know, we know kind of the shape. Let's do something more interesting. Like f of x equals 5x to the 2/3 minus 2 times x to the 5/3. What I'm doing here is I'm just pulling some even problems out of the section. Same questions as the last one. Part A, figure out where this function's going up. Part B, figure out where this function's going down. Part C, local max, local min. All right? Local max, local min. Start with the derivative. Okay, for this derivative, it's not complicated in the sense of it's not like there's no like quotient rule or chain rule. It's just power rule, right? You're just going to bring the powers out. You're going to do these individually. So power comes out here. When I do this times this, I get, what, 5? What's 5 times 2/3? 5 times 2/3. It's what? 10/3, right? 10/3. X to what power? What do we do to the power? We bring it down and then we subtract 1 from it. What's 2/3 take away 1? Negative 1/3. So we have negative 1/3 here. Okay? All right, now on this one, we bring this power, drop it out front. So what do we get there? Can we get 10/3 again? But it'll be minus, right? Because there's a minus sign there. So minus 10/3. X to what power? 2/3, right? You take 5/3, you subtract 3/3. 5/3 minus 1 is 5/3 minus 3/3, so 2/3. I don't spend too much time on that because power rule was like months ago, right? And we should all be somewhat comfortable with subtracting 1 from a fraction. You might have to do it on the side, that's fine, but any questions here? You got to get this right. All right? If this is wrong, everything else is wrong, right? Everything else is going to be off. So make sure, take your time, make sure you get this derivative right. So the derivative is what it is, and now we need the critical numbers. So we need to take this, we find the critical numbers, or critical points, however you want to say it. All right, so what do? We take the derivative, we set it equal to 0, and we take derivative and figure out where it doesn't exist. Ooh, this can be fun. All right, I'm going to do that right here. Let's start out with the derivative being 0. I'm going to have to, I'll do the derivative doesn't exist after this. So I need to set this equal to 0, don't I? All right. Now it's algebra time. This all comes down to algebra. So what I'd like to do here, and there's like, 50 different ways you could go about this. There's a lot of different algebra you can do here to make this work out. And the way I do it, you may not like it, but you need to have a way of doing it, like whatever, you need to find a way. So the way I would do this, I'm just going to show you the way I would do this. I would rewrite this as 10 over 3x to the 1/3 minus 10x to the 2/3 over 3 equals 0. So all I've done there is anything that's in the numerator, I've left it up in the numerator. Anything that's in the denominator, I've like pushed it into the denominator and made it very explicit, right? Like in front of you, you can see it. This negative exponent means I drop it down and it now becomes positive 1/3 on the bottom. The 3 was already on the bottom. Here the 10 and the x to the 2/3 are really together on the top, so I put them like that, and then the 3 is on the bottom. That's just my choice of doing it that way so that I can now get a common denominator. I want to put these two together. So to put these two together, they both have to have the same denominator, right? They already both have a 3. This one has an x to the 1/3. This one's missing an x to the 1/3, right? So I have to multiply the top and bottom of this by x to the 1/3. Let's do that. I'm just going to kind of force it in right here. X to the 1/3 there, x to the 1/3 there. Then they have the same denominator. This gives me 10 over 3x to the 1/3 minus, okay, what does all of that become? How do you put x to the 2/3 together with x to the 1/3 if you're multiplying? You add the exponents, right? You add the exponents. You add these two numbers together. 2/3 plus 1/3, 3/3. 3/3 is 1. So that's just x to the first power. So this is just 10x up top over 3x to the 1/3 equals 0. Right? Don't you add the exponents when you're multiplying? Like x squared, bless you. X squared times x cubed would be x to the 5th. You add the numbers. Here you're just adding fractions. Do they have the same denominator? Okay, I can put them together. So I have 10 minus 10x, those are the numerators put together, over the common denominator, 3x to the 1/3 equals 0. And now I told you something a couple of classes ago about when you have a fraction equals 0, right? You only have to worry about the top being 0. That was the whole reason I did all of this, is try and get everything into one fraction to make it look nice so that I can just let the top be 0 now. And that's a nice little linear equation. I can just move the negative 10x to the right and then divide both sides by 10. And I have a critical number. X is 1. So far, one critical number. As long as I can plug that number into this, right? Are there any problems with this? We never talked about that. Are there any domain issues up here? Maybe we should, let's address that real quick. What does this really mean? What does x to the 2/3 really mean? It means the cube root of x squared. That's what that means. And what does that mean? The cube root of x to the 5th. That's what those two expressions mean, right? That means that. This means that, right? Is there any number you can't plug in? No. It's a cube root, right? Not a square root. You can do cube roots of negative numbers, so you never have to worry about like imaginary numbers here. So you take a number, you square it, you take the cube root. I should be able to plug anything I want into that. Positive, negative, even 0, right? I can plug 0 into this. What's 0 squared? Cube root of 0? 0. So I can plug 0 in here as well, right? So we have no domain issues, right? There's no problems. So I can plug anything I want into that. And I'm getting 1 here, so of course I can plug 1 in there, right? Okay, am I done with critical numbers? What else? Where does it not exist? Okay, so let's let that be this section here. I'm going to say where does the derivative not exist? Right? Question. Well, my derivative, I cleaned it up real nice. Wasn't that my really nice, pretty cleaned up version of the derivative right there? Let's take that and let's look at that instead of like the ugly version. So my derivative looks like this. 10 minus 10x over 3x to the 1/3. I'm not setting it equal to 0. I'm just looking at the derivative, which is the left side. Does that ever have a problem? Is there any value of x you cannot plug in? What value? Good question.
It's just whatever that makes the problem.
Whatever makes the bottom have a problem. Is there a number that you could plug into the bottom to create a problem?
So, 0.
0. Right? What happens if you try and plug 0 in down here? Cube root of 0, right? That's what that means, cube root. But either way, 0 to any power is still 0. So you get division by 0, right? I can't plug 0 into this. I think this is one of the first times our derivative has failed to exist somewhere. We have an issue here, don't we? So x equals 0 is a second critical number. And it is a critical number because 0 can get plugged into that, right? 0 can go in here, but it can't go into that. If 0 was not allowed here, then we would throw this away, all right? But 0 is allowed here. Y'all good? We have 2 critical numbers. We've got about 13 minutes. I think we can finish this up. We have 2 critical numbers. What next? What's the next step? Number line. This is fun. Okay, third step, number line. Just make sure you get these in order. 0 first, 1 next. This has a natural partition of our number line into 3 regions. It won't always be 3, okay? It depends on how many answers you get here, how many critical numbers you have total, right? If you had 3 of these, you're going to have 4 regions. If you had 4 of these, you have 5 regions. If you have 1 of these, you have 2 regions. There's my number line. There's my regions. What next? Test points. Test points, right? Okay, what's a good test point over here? Negative 1. Could you have used negative 2? Yes. Could you have used negative 0.6256? Yes, anything you want, all right? Something between 0 and 1. Well, unfortunately, there's no nice numbers, so maybe just like a half or something. And then something over here. 2. Okay. Where do you plug those test points in? To the derivative. Remember, you told me that 3 times. You told me that, right? So the test points get plugged into the derivative. So that's my next step. Plug into the derivative. And I just erased it. Here's my derivative. I'm going to put the derivative right there, top right here. That's my derivative up there. This is f prime of x right here. Okay, so what I need to do now, 4th step, plug in test points. So I need the derivative evaluated at negative 1. I need the derivative evaluated at a half. I need the derivative evaluated at 2. The derivative, right? All right, let's plug negative 1 in here. If I put negative 1 right there, makes that a negative 10, but then a negative already. So that'll be a 10 plus 10 on top. That's 20 on top. Over 3 times, now this x to the 1/3 really means the cube root of -1, right? That means the cube root, and I'm plugging -1. What's the cube root of -1? -1 itself, right? Because the only number you can cube and get -1 is -1. So -1 times -1 times -1 is -1. So we get 20 over 3 times -1. But all I really care about is that this is what? Positive or negative, right? That's all I care about. What is it? Negative. A positive number divided by a negative number. I do not actually care about the exact value of it. I just care that it's negative. And now you have to plug in 1/2. Hey, question, what do you think? Can we just find the first one? And if it's negative, then it'll go positive, negative? What do you think? Can we just find the first one? No. We have to check because it might not switch signs. It may not. All right, let's see if it does. It could, but it doesn't always. So you have to check each one. If I plug a 1/2 in here, what do I get? What's 1/2 of 10? 5, and then 10 minus 5, we get 5 on top. And on the bottom, let's not overthink this. I don't even need a calculator to answer this. Because I know when I take the cube root of a positive number, I'm going to get a positive number. And then 3 times a positive number is still positive. And a positive divided by a positive is positive. So this whole thing turns out to be positive. So it did switch, didn't it? Okay. And now plug in 2. If you plug in 2, you get 10 minus 20. That's a negative number on top, negative 10. 10 minus 20. On the bottom, 3 times the cube root of 2. And same logic, it's a negative on top. This is positive. Cube root of 2 is a positive number. Who cares what it is? Times 3 is still positive. So you get a negative over a positive. This will be negative. So yeah, they switched, but don't count on it, right? Do not count on it. You have to test each one. Almost there. What does the derivative at -1 being negative tell us about the original function in this region? It's going down. So the original function here goes down. All right. What about the derivative at 1/2 being positive? The function goes up in here. And then at the end, from 2 on, it's negative. So the function goes down, then back up, and then back down. Right? I think I'm ready to get my final answer now. Part A, part B, part C. For part A, where's the function going up? Where's the function going up? Between 0 and 1. Okay, part B, where's the function going down? Well, to the left of 0, right? And to the right of 1. So to the left of 0, union to the right of 1. So from everything from the 1 over, and everything from 1 to the right forever, and then everything from 0 to the left forever. Mistakes I see students make when they do this is they'll accidentally put the test points in here instead of the actual critical numbers. That's why I circle my test points. I circle them so I don't accidentally use them in my answer over there. These are just for testing the derivative. That's all they're for. And finally, local max, yes or no? Local max? Yes, where? When x is 1, which means if I plug 1 into the function, I should be able to get an answer, right? So if I plug 1 into that, I won't go through the work, you get 3, okay? You get 3. And then local min is that x equals 0, so if I plug 0 into the function, the original function, I get 0. Remember, the fact that I'm saying that I have a max at 1 is not because 1 is bigger than 0. It's because it goes up then down. That's a maximum. Here, it goes down then up. So here's what we should expect when I type this in the calculator. Or the computer. We should expect a graph that goes down, then back up, and then back down, right? One more thing I want to point out. These were 2 critical numbers, right? 1, what was happening at 1? the derivative was 0, right? The derivative was 0. And then at 0, the derivative didn't exist, right? Which means it's going to look a little bit different at 0. Something else is going to be happening. I'm curious to see how Desmos handles this. Sometimes it has problems with these rational exponents. So the original function was to the 2/3, and then minus 2x raised to the 5/3. Oh, it did pretty good. Okay, let me go to a standard graph here. There's the graph. You have a cusp. Exactly. You'll see it. There's the graph of the function. So we have to the left of 0, it's coming down. Between 0 and 1, it goes up. And then from 1 on, it goes down. Here, at this point, we have a local maximum. And you can see there that at 1, the derivative is 0, right? Slope of the tangent line 0. But over here, this is a local minimum. That is the lowest point, okay? In that little area, that is the lowest point. But the derivative doesn't exist there because you have a cusp. But we're still able to find the local min, aren't we? Okay, so I hope that this example shows you, the power of the derivative. It all comes down to, can you take the derivative? Can you set it equal to 0? Can you figure out where it doesn't exist? If you can do those things, then really you can tell me a lot about what a graph's doing. Your homework for this, and I still have a few minutes, so you can pack up, but just hear me out here for a second. Your homework for this is I challenge you to try 25 through 35 odds, and only do parts A and B. Right? So part A says find the intervals where the function increases and decreases. All right? And then part B says find the local max and mins, which is exactly what we did here today. Now I know you're packing up. Give me 2 more minutes. I want to at least tell you about what's coming now. We're not done with this section. We're halfway through. The next idea is that if the derivative tells you about where a function goes up and down, does the second derivative tell you anything? Right? The first derivative tells you where a function goes up and down. Does the second derivative tell you something? And it does, all right? What the second derivative tells you is what's called the concavity of a function. So I want to show this to you. We won't do anything yet, but I still got you for 2 minutes. So I want you to look at a graph. All right? Now, you can look at that right now, and I think you